more examples in order like to fully understand that. So now we have a controller that we would like to design as an example in Verilog. So we have here a combinational logic. We have here a state registers, and here are the states, and here will be like some of the outputs and so on and so forth. So this is basically is implemented through that particular state machine. If you look closely here, this is the first state, which is called off, and it does have an output of x0. So as soon as you are in that state, your output will be x equal to 0. Okay, that's fine. But how I will move from this state to the other state? It tells you here that if you have an input called b, you will go to another state called on1, and basically your output will be x equal to 1. So if b is equal to 1, you will go here. But if b is equal to 0, you will keep yourself inside the same state. If b is equal to 0, you are still in the same state. If b equal to 1, you will go to the on1 state. Okay, that's fine. Then next, you are going to that particular state, and there is no depend on a condition. So basically from here to here, it's basically mealy machine, and from here to here, it is more machine. And you will go to n2, x is equal to 1. And then the next state, you will go to n3, and again x is equal to 1. And then the next state, you will go to a state off, and then x equal to 0. Okay, we would like to write that in the Vivado, or using the Verilog. How we can do that? First of all, how many states I have? 1, 2, 3, 4. Yes, 4 states. And for the computer to understand that I have 4 states, I have to define that I have 4 states. And I have to actually assign each of this state to a certain name, whatever I will call it. But since they are 4, so how many bits I need to use in order to differentiate between a state and the other? I need 2 bits, yes? Yes, 2 bits, because using 2 bits, I can have 4 different values. So I can say like this is state 0, which is 0, 0. State 1, which is 0, 1. State 2, which is 1, 0. State 3, which is 1, 1. So I have 4 different values. Okay, and this is what I did here. I have like defining some of the parameters. State off, state on 1, state on 2, state on 3, and each one of these is defined by 2 bits. How I define it as 2 bits, I say like, hey, this is 2. And then I'm using the binary representation, and this binary representation is represented in 0, 0. Please review the previous lectures, and you will see like an examples of how to write a decimal, how to write a binary, how to write a hex, and so on and so forth. But this is just like as simple as whatever like I'm explaining right now. I would like to use 2 bits, so I will write 2. This shows you like how many bits I need. And then I need to write that in binary. That's why I have used B, the symbol B, the letter B. So that's meaning that I'm using the binary, and what exactly the values are 0, 0, or 0, 1, or 1, 0, or 1, 1, as you see here. And of course, I have to define that I have a module, and this module I give a name. Inside that name, I have what we called here the sensitivity list. What does a sensitivity list means? Meaning that my code will be sensitive to any parameter or value or input that is basically inside that sensitivity list. And as soon as any of these values that is inside the sensitivity list changes, my output will be changes. Or my left-hand side inside the Verilog will be changes. Because I will say at the end that this output will equal to something, and usually equal to something that is a combination between some of the inputs, correct? And as soon as any of these inputs changes, if it is in the sensitivity list, my output will change. If it is not in the sensitivity list, unfortunately, if it doesn't change, the output will not change at that time. Okay. I have to define also that I have what we call a current state, which will be at the register. The next state will be at the register, which will hold any of these states. And since it will hold any of these states, I have to define them as also 2 bits, yes? So they have to hold 2. And since they can hold 2, so this means that I have to define them as a register, and it will be 1:0. Meaning I have like 0 and 1. So now I have like 2 bits to represent that. Okay, that's fine. Let's begin with the easy stuff first, which is basically that part, the sequential part. As we mentioned, the sequential part will be always that the current state, the next thing will be the next state. But I have like to add like some salty and pepper stuff in order like to make things like much or looks much better. What it will be like the salt and pepper and all of these things that I'm using here, that I have to use the reset. And that's why here I say like, hey, if reset, please reset my state. Otherwise, always your current state will hold the next state. Correct? And this is what I am showing here. I'm saying here, if reset is equal to, sorry. If reset is equal to 1, please, your current state now is the beginning. S_off. Else, your current state always will hold the next state. So this is what it will just like govern the sequential part. However, we need to write the combinational part, because basically the combinational part what will hold all of these details, as we will see now. So we have to write another module which have like an always block again, and then inside that always block, actually I have the sensitivity list at the current state or my inputs, which my input here is basically B, and then I will begin to hold any of these states one by one. First of all, I told you that it is much better to use a case statement more than using an if statement, and that's why we will begin with a case statement. What is that case statement? Will hold basically the current state. Okay, so let's hold the current state and we will go over each of these states. Let's hold that this is, as an example, the beginning of the current state. Later on we'll hold this at the current state. Later on we'll hold this at the current state, and so on and so forth. But let's begin now with this S_off. S_off, I am here right now. Begin. What will happen if I am at that particular location? X is equal to 0, correct? This is what I'm writing here. X is equal to 0. Okay. Then what will happen? What we are saying just by our tongue. If B is equal to 1, go to the next state. If it is B equal to 0, stay in the same state. This is what we need to write. If B is equal to 0, please, your next state is still the same. S_off. Otherwise, else, your next state will be what? On 1. S_on 1. Agree? Then, now we are in which state? The next one, yes? So let's see like the S_n1. So we will see S_n1 begin. What happened here again? X is equal to 1. X is equal to 1. Do I have any condition to stay here or to go to another one? I don't have any condition. So basically, always my next state will be the S_n2. Correct? Always will be S_n2. Okay, now I am in S_n2, as you can see here. What is happening? X is always equal to 1. X is always equal to 1. And then my next state is what? S_on3. S_on3. So now I am here. Let's see like the S_on3 again. the x is always equal to 1. So the x is equal to 1. And then what next state is? The off state. Next state is the off state, end the case, and then end begin. And then end the module. Okay, here is just like another example of finite state machine. Again, we have defined these parameters with S0, S1, and S2 as an example. And again, the case statement, here I have it as the state. And then we'll begin with S0. Begin, if start, the next state will be this, else the next state will be this, and so on and so forth. So we are following exactly the same things with the combinational. And then the sequential is here with the always block, always state will be equal to the next state, and so on and so forth. In the quiz or in the exam, I can give you like a state diagram and I ask you write it, or I can give you this and ask you draw that. So it can be any of these things. You have to go from one to the others, and so on and so forth. This is also another example of a finite state machine. So you will define like some of the parameters here, but then you are using now 3 bits instead of 2, and then of course you define that this is 0, 0, 0, this is 0, 0, 1, and so on and so forth. And then at the always block at the positive edge clock, and again positive edge clock means like that. If this is negative edge clock, so this means that it does change the output if I have a negative edge clock. And again, it shows you if I have the case state sreg, and this state, it can be initial, it can be A0, it can be A1, and so on and so forth. And each of these states, you can think of this the same way, that if A is equal to 0, the S next will be this, else the S next will be that. But there is an important difference between whatever I wrote here and between I showed you in the previous 2 examples. I will highlight that. But before I highlight that, if you look closely, this is basically the sequential part, which is basically the state is equal to the next state. And this is the combinational part, as we mentioned earlier. But here I have another always block. What does that always block really do? It actually split whatever like you are doing with the states and whatever you have with the outputs. Meaning, if you remember in the example that I just finished, when we have like x equal to 0, yes, and x equal to 1, let's go back to remind you. We have here x equal to 0, x equal to 1, and so on and so forth, and we wrote that inside the combinational, yes? If you are here, x is equal to 0. If you are here, x is equal to 1, and so on and so forth. But actually, there is another smart way in order like to do exactly the same thing. That I will take all of these output and will write that in a always block. How I can do that? I will create an always block and say like, hey, if you are in this state, x is equal to 0. And if you are in this state, and this state, and this state, always x is equal to 1. So I will write just in 2 lines inside another always block, without taking care each time what exactly the output, and so on and so forth. And this is what we have here. If you look closely, you will see like, hey, none of the outputs already I mentioned here, and the output is here. And basically I'm saying that if you have, or if you are in this state, or if you are in this state, or if you are in this state, always the z output is equal to 0. If you are in this state, or you are in this state, always the z is equal to 1. The default, the z is equal to 0. So this is another way. And again, I can give you this in the exam, and I can ask you to draw the state machine. And I can give you with this syntax or with the other syntax. And you should be familiar with this or the other one. Okay? There is also here another finite state machine example. Please go with this by yourself. It's just following exactly the same concept that I have described with the previous examples. But I have included for you, like, in order like to see like how we can write a more complicated finite state machine. So now we will move to another important thing, that okay, how we can use the Verilog in order like to write an SRAM or using a flip-flop. By default, the flip-flop I can write synchronously or read synchronously or asynchronously. So this is with the flip-flop. However, with the SRAM, I can do exactly the same. However, I can't read asynchronously. What is the difference between write or read synchronous or write and read asynchronous? So basically, when we are reading synchronously or writing synchronously, so this means that we need to have a clock in order like to govern actually all of the writing or reading from or to into the memory. However, with asynchronous reading, meaning as soon as the address is changing, then I will begin to read at the output another values, as we will see with a lot of examples shortly. So this memory reads and writes. Writing to the memory is always considered to be a synchronous operation, which is like occurs synchronous to the clock. However, with the read from a memory can occur synchronously or asynchronously, and this will depend on the style of the memory. So let's take an example. Assuming that you have now a single port memory, and this memory has an input address, has an input called data input, has an input called write enable, sorry, not we, yes? Write enable, and a symbol, an input here called the clock. And you have an output that's called data output. And I would like to write now a Verilog code that will describe first that I have a memory, and this memory with that particular size, and that particular memory has these inputs and output. And then I need to write inside the same code that how I will write into the memory and how I will read from the memory. Why I need that? Because actually, as I mentioned earlier, that our ultimate goal at the end is to have a mini CPU, yes? And inside this mini CPU, of course, I have a RAM. Correct? With everything. You are building everything actually inside that. Or you will have like the register, which will also be designed with the same concept. Okay. Remember that I have input address, data in, write enable, clock, and I have an output data output. Okay. This is how we write the Verilog. We have first define a module, and then I define that module. Then I have to define first what is my inputs and outputs. If you recall my input, this is a clock, write enable is an input. I have a data input, I have an address, and I have a data output at the end. Of course, the data input and the address, it's again an input. However, this data input is basically 32 bits. And if it is 32 bits, I have to define them that they are 32 bits input. So I have to write that it is 31:0. I have also another input that's called address. And with this address, we have it as an 8 bits. And since we have it as an 8 bits, I have to write also that this is only an 8 bits. And since I have an 8 bits, I can address all the way till 2 to the power of, yes? 8 and then minus 1, yes? So you can go all the way from 0 to 55. And your data output, it is output, and again it is 32. Okay, why we define this as reg here? Because if you review the videos, you will see that I mentioned that if I have any values in the left hand side of an always block, I have to define as a register. Otherwise, you will get an error. Okay, so now we know that why this is defined as a register. Then I have defined now all the inputs and the outputs, but I need now to design my memory. What is the size here and what is the size here? I can call this RAM, I can call this memory, I can call this ROM, whatever I would like to call it, but I have to define it. So I have defined this as a register that is 31:0, and then the name, and it is 0 all the way till 255. What does that line mean? This means that I will declare a RAM that is 256 entries and the width is basically 32 bits. So each entry is 32 bits. So I have 256 floors, and each floor has 32 rooms. Now you do understand, yes? So you'll have like all of these slots, 256 slots. Each of the slots can contain like 32 balls, or 32 bits, or 32 rooms. Okay. So now here, all of these, I'm just defining whatever I have. I did not define how it works. I just define, hey, I have a RAM with this size. Hey, I have the inputs and I have the outputs. But I did not say like how I can read or write this data. And this is what we will learn. Okay, I would like, as an example, to synchronously read and synchronously write. If I'm telling you that I would like to read and read synchronously, so this means that I will use the clock with either read or write. Okay, so let's see like how we can do that. First, always block. Again, inside the sensitivity list, I should have the positive edge clock when I write, and I should have the positive edge clock always when I read. Okay. If you remember, one of the inputs is the clock, but there is also another input that is called write enable. What does that mean, write enable? Means that you won't be able to write unless you have the write enable high. As an example, if I say like it is active high. And I won't be able to write unless I have the write enable high and I have a positive edge clock, as I mentioned here. So if I have a positive edge clock, I will go to see, do I have the write enable high or not, 1 or not, or maybe the other way, 0 or not, whatever like I will do, which one is active. And then if I have a rising edge or a positive edge clock, and then my write enable is high, please now write inside my memory. Okay. If the positive edge clock, and then if write enable, please write inside my RAM whatever I have in the data input. And where I will write inside my RAM, I will write inside my RAM at that particular room number. So I am telling, as an example, my part here, that if you have here a data, yes, that data will be written in this particular address if I have a positive edge clock and I have my write enable is high. And then I will be able to write whatever I have at that particular location to whatever I have at that particular address. So I'm telling you, please go to the slot number 50. And inside slot number 50, please write all of these values. And there is no relation between the values that I will write and the address that I am using. Yes, it doesn't have to have 50 also value. I can write to address 50, whatever I would like to write, but it will hold all of these 32 bits. And that's why I'm saying, hey, inside this RAM, under that particular address, RAM of 50 or RAM of 49, since it is the 50 slots, RAM of 49, please write whatever you have at your input or data input. Agree? I need to think again the same when I would like to read. I would like to pull something. So I'm telling you, please go to that hotel, to that particular floor, to that particular room, and begin to bring some stuff. Okay, so this means that when you have this stuff, it will appear at, again, another thing here is called the data output. So the data output, which is that guy, will hold, as an example, the memory address 45. So I'm telling you, show me here at that particular output whatever you have at RAM of 45. So at slot 40, basically 6, yes? Because I write 45, so it is at slot 46. Show me all of this output in the data output register, or the data output. And if I can do that, then you will take at this particular data output, again at the positive edge clock, whatever you have at that particular location.
If the RAM is too...
So let's see, like, okay, so now we write synchronously, and we already understand how I can write synchronously. But then if I ask you, like, read asynchronous, with reading synchronously, we just mentioned that we have to have an always block with positive edge clock, and as we just saw. However, if I'm telling you, no, I will stick with reading asynchronous. How I can represent that in the Verilog, this is what it shows you. I will just assign whatever I have at the data output to that particular location. So this means that as soon as that address change, the output will change. So if I am changing the address, then your output will change. Why? Because now I am pointing to another slot. So if I'm pointing to another slot, I'm saying here assign. I didn't tell you, like, please wait until you have a positive edge clock, or until you have a negative edge clock, or until whatever, like any other signal. I'm just assigning always that output will hold whatever the address is pointing to. So if I'm pointing to the slot number 50, so now I'm pointing to slot number 50. Whatever in this slot will appear at the data output. And then now I am pointing to the slot number 10. Okay, so slot number 10, what is inside slot number 10? There is a data, yes? There is a 32 bits number. That 32 bits number will appear at the output. Now I'm moving to this. I'm moving to this. I'm playing, yes? Yes, and each time I'm doing that, I have another value at the output. I don't have to wait to any clock, because I have designed my RAM to actually read from its port asynchronously. And as you can see, this is the beauty of the Verilog. If I were, as an example, to begin to ask you, no. Begin now to design all of these things with the logic gates. Oh, this is really difficult, because now you have, like, to design the AND or 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 NAND, or how you will combine them, or you have to write a truth table, and after you write a truth table, you have to have the kernel map, and after the kernel map simplification, and then you have to build, like, a big circuit, and then to begin to implement all of these big circuit inside your design. However, with Verilog, you don't have to do all of these kind of things. You just write, if this, do that, if this, do that, and this is how you control whatever, like, the values between the inputs and outputs. And this is the beauty of this tool. I mean, if you were, like, to go, like, 20 or 30 years later, when people, like, begin to think about that, we need to have a tool that will actually make things a lot easier to the designer, you will appreciate all of these things. Because I have seen, like, in one of the companies, when just Verilog was just, like, designed, and at that company they didn't know, like, the Verilog, and unfortunately, I mean, millions of gates. And I was like, oh, really? How you trace all of these things is completely difficult. I mean, this is what we used to do, like, all of this 20 years ago, and Verilog is only available now, and we will begin to learn it. But all of this is our past experience. Okay? Are you guys like still wake up?
Yeah.
Sure? Okay.
I could use a story.
Next time. As I mentioned, I will share. I have a lot of stories, so we'll share with you a lot of this kind of nice stuff. So today is just like the train, yeah. So
Will they be on the exam?
of course, to differentiate between like people already there and people like who did not, because this is not in the recording, yes. So please tell me what was the country that the professor faced the problem of the train. Then I will be very easily like to differentiate between students like who attend, yes, without taking the attendance, yes. And then +5 for everyone who got the correct country.
For a sign, does it constantly set data out as the
Yes, so whatever I'm pointing to, it will show that at the output. So now I'm pointing to the slot number 2. Whatever is in slot number 2 will appear at that particular output.
So it doesn't need to register a change in the address before it
You actually don't need to worry about that. It's just like we represent it that way. And when you go to the simulation, you will see as soon as you change the address, the output will hold the data that is available at that particular slot. Okay? So now we will go to a dual port memory. So now we have write address and read address, meaning that I can write to a certain address and read from another address. So I don't have to use exactly the same things, yes? I can write to address or slot number whatever 10, and I can read from slot number 5, or whatever the way I would like to do. Again, I have write enable, I have data input, clock, and data output. Okay, so let's see like how we can write that in Verilog. Again, the same exactly concept here. Till here, I'm doing exactly the same. Nothing changed. Yes, I'm defining the inputs, the outputs. I'm defining whatever the RAM that I have, 256 slots, and each of these slots is 32 bits. And again, I have to write synchronously, so basically positive edge clock, and I have to read also synchronously, so also positive edge clock. So this is exactly the same. Everything is exactly the same. The only difference that this guy will not hold only the address, and this guy will not hold only the address. It will hold the corresponding address. Meaning, this guy will hold the write address, and this guy will hold the read address. Because actually, I will have like two inputs. Yes? So whatever I will read from whatever that particular address is pointing to. So I'm pointing to address number 5. Okay, so show me whatever I have in that particular address. When I will write, I have another address that is pointing to another place. They might be the same, or it might be different. So if it is different, so this means that I am writing now to the second slot, but I am reading from the 5th slot. And that's why I have to have these values not exactly at the same as these values. Agree? How I can do the same exactly thing, but I am synchronously write, but asynchronous read. Again, I will do the always block as I mentioned earlier. However, with the data output, which is basically reading the asynchronous, I will assign the data output that is equal to the address that I'm pointing to. I am pointing to, please read now from slot number X. Okay, so slot number X, it will appear at that particular output. Slot number Y, it will appear at that particular output, and so on and so forth. I don't have to wait until I have a clock, or until I have a positive edge, or negative edge, or whatever the clock that I'm using. Okay? I will always have these kind of things. I think I will stop today at the true dual port memory, which we will cover next time. Thank you so much.